Okay, welcome everybody. My name is Christine Perret. Very pleased to have so many people joining our webinar today. This is the July 15th Research Committee webinar. And we're very, very pleased to have Dr. Rafael Radkowski come and join us from Iowa State University to tell us the kinds of research that he's doing, he has done in the past 5 years or so, or maybe longer, and how he's the kinds of things he's working on at this time. The purpose of the area research webinars is to inform everybody about active research that is relevant for enterprise use cases with AR. And it's my pleasure to turn it over to Rafael, and he will introduce himself. Thank you, Rafael. All yours.
Thank you very much. And good morning and hello, everybody. Welcome to this webinar. It's a pleasure for me and an honor for me to be here this morning, or depending on where you are in the world, this evening, and to talk to you about my research and introduce my research topics and the lab, and in general what we do here in this lab. Before I start and dig into research projects, I have a few examples. I would want to talk and introduce myself. Here we go. I'm an assistant professor at Iowa State University since 2014 with appointments in mechanical engineering, computer engineering, and computer science. I'm originally from Germany. I arrived at Iowa State in 2012, 2011, around this time, first as a postdoc. Before this time, I spent a lot of time in Germany after I graduated, working as a senior research associate at a collaborative research center. It's a larger group of researchers, and we address topics like, we would today say AI systems, making AI systems safe for engineering systems. How do we communicate with modern AI systems, and those things. Before that, I was a PhD student at the same university and worked with neural networks and training neural networks in virtual environments and similar topics. Today I'm at Iowa State University. I'm part of a larger center, the Virtual Reality Applications Center. So this picture here shows our building. We have the majority of the left part of this building here. It's a larger group of researchers, and the topics that the center addresses, it's not only virtual reality, it's all about virtual reality, mixed reality, augmented reality, human-computer interaction, and these topics. We are home of the C6. The C6 is a cave, 10 times 10 times 10 feet large cave. So it's embedded into this sculpture that you see here. And I'm right now behind this big window here, which I framed with this white picture. So let's have a look into the lab. So the lab is inside the building. That's the picture of the lab as of this morning. I took it very early, so you can see the students around. So that's part of the entire lab. So we focus in this lab on vision-based tracking and registration with focus on augmented reality. So we have a lot of iPads around and other tablet computers that people would use for augmented reality applications. Also a lot of other range cameras, industrial range cameras, and so on. My research mostly addresses manufacturing, training in areas like aerospace and manufacturing in general. I have a few defense grants working on defense-related topics. So currently I have 8 graduate students in the lab, 3 PhD students and 5 master students, and I believe 12 undergrad students. I usually use track about the undergrad students, but I think these are 12 undergrad students. So our entire lab is equipped with plenty of cameras. As you can see here, we have cameras underneath the ceiling, like Kinect. We have an AR track system, so we can track objects in the entire lab if we like to. We have a breadboard for smaller experiments, for any type of experiments that we want to use. We have parts of an airplane in the lab, an electronics equipment side, and so on and so on and so on. So in the research that we do in this lab, as I mentioned, is all about 3D computer vision and tracking. So in particular, I focus on tracking in 3D point clouds. Here tracking, when I talk about tracking, I mean the continuous pose estimation, 6-degree of freedom pose of a physical object with respect to the camera in general. And we focus in particular on real-time tracking and on very high accurate tracking. So the precision or the accuracy in millimeter or inches should be very high. And point cloud, as you can imagine, we have RGBD cameras, and they allow us to generate point clouds of our environment today. So the tracking that we work on is also some sort of model-based tracking. So we need a model of the parts that we want to track. Most often we use CAD models from partners, or we scan them with a range camera and create a 3D model. And then we are able to identify this part in our environment and can track it with in-camera frame time today. That's what we focus around. We address different topics like object registration, pose refinement, pose accuracy, removing noise, removing effects of noise, and so on. Everything around those two topics, getting something accurate and make sure that everything what we do also really works in real time / here camera frame time. This video just shows a small example how it may look like. So this is now a video from the lab. The data that you see here, the red points, these are Kinect points. There's here a person who moves a table around. It's a manufacturing fixture, or it's a cart with a product attached to it that people on the factory floor move from assembly station to assembly station to assembly station. And what you see here is basically how we are able to track it. I will talk a little bit more about how it works, but yeah, to make those things possible, that's what we do in the lab. We also focus on robustness. So we have applications with partners in industry. So we deal a lot with robustness, occlusion, clutter in the area, and just make sure that what we do also works. So everything what we do in the lab also rotates around one tool that we have. We call this tool Tracking Expert. That's what you see here on the slide is the main interface. Don't judge the interface, it's just it's a grown tool. So we started this entire tool in 2011. I believe even earlier. There's still sometimes source code inside, which comments and notes written in German, so I have to translate this for my students. But the main development of this tool started in 2011, so it supports tracking of objects. It's basically an authoring tool, so you can decide which cameras you want, 1 camera, 2 cameras, 4 cameras. You can load an object that you want to track or a reference data set. Then it comes with a lot of graphical user interfaces or widgets for settings to prepare the entire tracking experience, let's call it this way. And then you can start tracking. So it comes within this interface version. It also comes as a library. So usually in plenty of projects, we just make our experiments using this tool. Then if we write a particular application for a partner, we usually embed the library, and then we can use it. So it supports multiple cameras, different cameras. It comes with descriptor matching, so feature descriptor matching, iterative close points for refinement. We can measure the pose of an object with very high accuracy. We can extract a surface and measure the surface with very high accuracy. We can compare the surface to a reference surface. It has plenty of filter installed, bilateral filter to smooth the point cloud data, sampling filter, and a lot of other things. It has, in general, project supports, so everything is based on product. You can define projects, tracking projects in this entire tool. And everything is CUDA based. So the majority of things that we do work on the graphics card. That's the basic process behind the techniques that we use. I will not go into details here, so everything is published, or if you want to have more details about things, you can feel free to contact me. But it implements, or Tracking Expert implements, a 3-step tracking process. Input is a point cloud from a range camera and a reference object like this one here. So the green object is just a visualization of a reference object. Red one is what we get from a camera. So then it's always the same loop, 30 times per second. So we detect the object, usually using some sort of feature descriptor matching process. Here we get this feature descriptor from the CAP model, as I mentioned before. If as a reference model, feature descriptor matching is very sensitive to outliers, so we usually get a rough estimate where the object is in our point cloud, so we have to refine this. And once we refine this, we track with a Kalman filter to reduce the effect of camera noise and other effects. We have an optimization model, a Gaussian mixture model embedded, which we use for very high accurate tracking, for a very high accurate pose estimation in this case. That's how it technically works. So in this entire tool, we use it in all our applications. And one of the most popular applications that we support is, of course, assembly assistance. So that's how it works here. That's just an example for this piston motor. So you see this reddish greenish object that superimposed our piston motor. So this means the entire part here is tracked because we can move it around. So, and then, yeah, I think everybody knows the scenario. We can superimpose 3D model, align those 3D models correctly, spatially correct with the parts that we track, and yeah, indicate or convey assembly instructions this way, like here, assemble the shaft. So just a few steps, so this is not the entire piston motor. So there's a gasket that comes next. Here, the end cap. Yeah, it's a little bit tricky to install this piston motor, how to assemble it. So, and the bolts. Come next. So the entire video here was recorded from a display. And so you can observe those instructions on the display, but that's not the ultimate goal that we have. So usually we want to use tablet computers or head-mounted display. So Tracking Experts also supports those devices. It runs on a Windows surface with limited performance, but it runs. But we can also connect it to a Microsoft HoloLens. So not directly, but so one of the devices that we have in the lab is, of course, a HoloLens. So I believe I don't need to introduce the HoloLens here, but it's a headset, see-through display, and it can populate the physical environment with virtual instructions. So the HoloLens cannot track individual objects. It can track itself in the environment, but it doesn't know where individual objects are. So with our techniques that we have or that we work with in the lab, we can track individual objects like a piston motor and others. And Tracking Expert is prepared to forward those information to a HoloLens, and then the Unity application on the HoloLens, we can use it as a renderer and superimpose all this information that you saw, the 3D information via the HoloLens. So a user sees those things through the HoloLens. So these pictures that you see here, these are just screenshots with the graphical widgets here. The 3D model shows those instructions, but the user here sees those things through the HoloLens. I will not really go into details, but the entire thing needs a lot of calibration. So the slide here shows all the transformations that we have involved in that. So we have to, the HoloLens needs to know where the Kinect is, or not the Kinect, sorry, our main origin, coordinate system origin that we have to calibrate. So because it's our tracking calibration system, so we can use some HoloLens features that it provides to tell it where our main origin system is. And as you know, the HoloLens tracks itself in the environment. So once the user starts an application and runs around, the HoloLens tracks itself, and we can use the information to render 3D models via the HoloLens from the correct perspective. That's what we do, and that's just a small video that shows you how it looks like. So this video was recorded with a HoloLens, so you can say, hey, Cortana, take a video, and Cortana takes a video. So that's why you see a small offset. So the camera that the HoloLens uses an own renderer, so it has an own rendering component or an own image compositor. And this image compositor, if you just render the images that the people see through the display with this image compositor, those 3D models look like they are off. The experience the users have, it's perfect. As you can also see, we can move this entire object around. And so it's tracked with an external camera, and the information is forwarded through the HoloLens. There's a slight delay which comes from Wi-Fi, so it's a Wi-Fi connection. We just forward all the informations. But as you see, they come a microsecond late. So, but this is a technique. This works in the lab. So as I mentioned at the beginning, we don't only use those techniques in the lab, we also apply them and have multiple partners in industry which needs those capabilities. I want to briefly talk about one of those here. This is one of our installations that one of our partners has. It's, in this case here, it's Danfoss, Danfoss Power Solutions. Their name's Iowa, and I think in a lot of other locations around the world, well, they produce those pumps and piston motors, so they can turn fluid into rotation energy and vice versa. And what you see here on the right, these are pictures of a training station that they have in the facility. These are just small, tiny little pictures, crop pictures. I cannot show the entire training setup, but I can show those tiny pictures. And what you see here are renderings also produced with the HoloLens. So they have one of those systems in the lab. And they can use the HoloLens and can give it to their employees, and the employees can learn how to use this entire equipment, how to assemble one of those piston motors via HoloLens. They also get voice commands, so the HoloLens talks to the employees and shows them those graphical widgets. So what we have done here is, so we track all the essential parts. So a lot of parts are static. They don't need to be tracked. We just need to register them once and need to know where they are. But there are also a lot of moving parts. And especially this card that you saw before here is one of those moving parts. So usually how this entire assembly procedure works is that an operator or mechanics on the factory floor takes one of those cards, goes to one of those assembly stations, does something at this assembly station, assembles everything on this card here, and then moves this card to the next station. So what we can do with the Kinect here in this case is we can track those cards while those people move the card around. And we can track parts, moving parts on this assembly station, and guide the people to tell them which part do they have to take next and what they have to do. So the next video shows how it works in the lab. It's again just a lab video because we cannot show the original one, but that's the card here. These are just demo applications, demo 3D models, how it looks like. So the upper 3D model now would tell an operator, hey, assemble this lower body part onto this card. And as you can see, we can move the card around and the entire rendering stays put. Again, there's a slight delay, which is a Wi-Fi delay that we get here into the entire thing. Also, this down here, this is a swash plate that goes into this piston motor. There's some other parts missing. So it would go into a shaft and so on. And I think there are still a few more parts missing, but we can tell the people very precisely where they have to install those parts. The entire application is also a large area tracking application. This tiny picture here should indicate that. Here in this case, we can use just 2 Kinects. We can use up to 4 Kinects or other cameras and even more, and combine those point clouds, filter them, sample them, and provide those features in a larger area, and track objects in a larger space here in this case. So, and this is all what our application that we have supports. So object tracking, so you can track multiple objects as long as you don't run out of computer performance. Then it depends on the complexity of those parts. We can attach multiple cameras. We can attach multiple Kinects. We can forward those information to a HoloLens. And it also runs, again, on tablets, at least on Windows, Microsoft Surface, and with a range camera attached. And the good thing is the entire tool will be open source soon with NIST support. So not this version, so you will not get this interface, not this ugly one. But this entire tool will be available as an open source version on GitHub, so everybody can download it, use it. It will take a while until the entire tool with all features will be available. This will happen at one point next year, so the HoloLens support will come next year. But the first version, at least with tracking support and some other features, should be ready. We plan for August, so, and I believe we will keep the schedule that we have so far. So then it will be on GitHub in my GitHub account. So just pay attention. We will announce this at one point. Maybe via NIST. Maybe we can use Area to announce that. I will definitely post this on my webpage. And if you have any question, just send me an email, then I can keep you up to date and tell you where you will get it if you like to get it and test it. So this is the tool that we use for most of our research. So let me go to the next topic. I will not really talk a lot about studies here because I don't do them only on my own. It's most of the time in a larger group, and I believe some of the audience already know the study here. So, but that's also one of the things that we do here quite often at Iowa State University in larger teams. So user studies with augmented reality, comparing graphical widgets, which widget conveys an instruction best. So why do I point this out here? So my belief is with augmented reality, and what we are working here towards is basically the obliteration of user studies. Not immediately, but I believe that augmented reality needs to be at one point, at a point where user studies for single setups are not necessary anymore, so that we at one point have a catalog maybe of instructions, and we can just go and use this catalog and say, hey, if we have this instruction or this skill, or we have to train this feature or this skill, we do it this way, and that's how we can do this, and we can be sure that the people will understand those instructions. That's what we're working towards too. So all our user studies also feed our research, and again, that's not only my research, but it feeds our research into so basically user study-less augmented reality. The reason why we do this is because in companies, if you have paper manuals today, or if you have computer-based instructions today, to my knowledge, at least at our partners here, they don't run user studies on those, but they run user studies on augmented reality. And again, this should not be necessary at one point anymore. So what we started here at one point a few years ago, and we do this again and again, is something what we might can call skill-based instruction. So this name changes very often because we don't really have a good one. But what we believe is that the instruction and how we convey instruction, the complexity depends on the part itself. So is this a significant part, an important part, or is this just something that's less significant? Maybe a screw, something where an operator knows how you would fasten this, how you would assemble this. Maybe it's just a support part, it's not the main part, and so on. And we also need those instructions then per skill that a user should be trained on, or an activity. For instance, this is here just a tiny little excerpt of what we did in this for assembly, for instance. So we just at one point said, okay, let's just split all the assembly tasks that we have in those different skills and activities that the user needs to perform. Something like part identification, alignment of parts, joining of parts, fastening, quality control, and a few more. So then we have significant parts, which are the most important parts, and less significant parts. Again, maybe just a nut goes into a hole, and a bolt goes into a hole and needs to be fastened with a nut. The part itself for the component is important, but every mechanic who has done this for hundreds of different parts will know how they did this. And what we said always is then, okay, we need two different set of widgets. One widgets might be just graphical 3D models, as we do this today most of the time. And for everything else, we might just use very simple indications, something like an error. Yeah? For instance, if we want to instruct a user to put two tiny little rings into holes here, we don't need 3D models for that, because there's no mistake that the person can do. They need to go in. It doesn't matter if they flip them, they just need to know that they have to do that. So we just said, okay, we indicate that, and convey this instruction this way. So the entire thing is not ready, but one of the goals here is to have something like this ready at one point, and to give people who want to work with augmented reality and want to work on conveying instruction with augmented reality, to give them a manual at hand and just tell them, for this skill, do it this way. We have tested this so often, we can tell you it will work, and you don't have to rethink and redesign your user interface anymore. And you don't have to run a user study on the factory floor. Again, that's a goal, but we're working towards the goal. So now let me switch areas again. Back from assembly with augmented reality to inspection and digital twin. So since a few years, my lab works in the area of inspection with the digital twin. And what you see on the slide is a concept drawing for what we intend to do here in this entire area. So first, the digital twin, if you're not familiar with this, is what it says. It's a digital twin of the real product, This incorporates that it has all relevant product relevant states embedded. So it's the shape, it has actual data. So it's online connected, it knows about temperatures, it knows about flaws, failures, and so on. So it's basically the digital version of the real product online connected. So the digital twin already exists in the inspection area, mostly in autonomous plants, so in areas where you have a lot of automations, because if a digital model knows a lot about the physical asset, you need sensors. You need sensors to read real-time data from a product, and if you have a plant with high automation, I will not say that's easy, but it's a very feasible task. So we work in the area of manual inspection. So where, for instance, an inspector on a tarmac uses an ultrasonic probe to detect cracks in the airframe or fuselage of an airplane. Yeah. So you have your physical product here, an ultrasonic probe or an eddy current probe to detect cracks or corrosion. And they are usually hand-guided by an inspector. So to get this data into a digital twin model is quite hard, because you don't know where the probe is with respect to your physical product. So where do we come in place here? So the first thing is, now what we can do, we can track those equipment. So we can put a camera somewhere and say, okay, we track the ultrasonic probe, we track the physical asset. And this allows us to calculate the spatial relation between physical asset and probe. And when we get ultrasonic data or eddy current data or sonography data, which are the inspection techniques we work with, then what we can do is we can associate this data, the data set, to the surface model of, or to the shape model of a digital twin. So once we have this data, the future goal is then, of course, to analyze the data and to decide what we should do, but this comes later. So we are currently in the process of integrating this data and so on. So, and with augmented reality, what we can do then is we can visualize all the inspection data, cracks, corrosion, and everything else, which might be invisible. Delamination might also be invisible, with a head-mounted display on the asset, on the physical product. And of course, we can also indicate inspection location and guide an inspector from point to point to point to point to point. So as I mentioned, we started in recent years, so we focused first on tracking, and we start now to think about visualizations. So this was a small scale test setup here we started with flash thermography. So what you see here on this picture is a composite specimen and a flash HUD. There's a thermal camera embedded and flashes. Those flashes induce heat into a material. If there are holes in this composite material or delamination or cracks, this changes the heat transfer rate, and this the thermal images can show that. So, and what we can do is we can track the flash HUD, we can track the specimen, and here on the right one, you see the digital twin. It's a 3D model in this case, and the red area here is the thermography data, and here you see those points. These are delaminations. So, and of course, if this would be a fuselage of an airplane, we can do this again and again and again and again and again with this flash HUD and stitch a 3D model superimposed with thermography data together, and then an inspector can watch this directly on the fuselage so that you know exactly where your problem is on the fuselage. So that's just a video. I will just play this here. And that's our point cloud. The tracking technique behind this is somehow more complicated. The calibration technique is more complicated because we really need to be very accurate here, and this system has a lot of moving parts. So here comes the specimen. So we now track the specimen here. We don't measure the while we move it, so that we can track it, and so it needs to rest to get the very high accurate pose. We do the same with the flash HUD. Here it comes. Yeah, we have to load it. Used to load it manually. So just move it a little bit forward, fast forward. We just move it around to show that we can track it. We don't really need to move it for the application. So then we wait for our flash, it comes, and then we get our data, and it's embedded. So I'd like to show a few results of that, because we were really proud of the accuracy that we can achieve with the camera that we have here. What you see here, this is this U-star specimen with this is grayscale data superimposed on it. So we replaced the thermal camera with grayscale data, so it makes it easier to identify landmarks. So we used visible landmarks on the specimen to determine the accuracy here, and those yellow cross marks show us, or this purple cross mark show us the location of those landmarks. The landmarks is here a hole, and there are here some artificial landmarks, this grayer zone. I hope you can see them here. This light gray zone, and with our tracking technique and the calibration techniques that we use here, we can get this to ±10 millimeter, most of the time even better. The spread is a little bit high, but that's high enough, good enough to find delaminations on those parts and to identify them nicely. We did the same thing for ultrasonic tracking, also first on a small scale. You see here is we track an ultrasonic transducer in 3D, so there's a point cloud behind this. A calibration specimen, because we know the flaws on the calibration specimen, bore some holes and a cutout. Those points that we see here are the measurement points. We just measured points, so we cannot really paint everything right now. It's just how our ultrasonic inspection technique works. So somebody has to press the button all the time and say record data, record data, record data, and then the scope writes everything into a file. But then what we can do is we can take those points, and so these red dots here are the holes in our part, and this is a cutout, at least the points that we have. So we can right now not online paint it, but this is going to come. So that's what we already have here in this. So we are now in the process of going big. That's here future inspection. So we are not right now at this point, but we move beyond our small specimens and got now 50% of an airframe in the lab. It's 9 feet long. So now we will work here with eddy current inspection, ultrasonic inspection on this part. So what this person does here is right now, again, it's not ready yet, but this is how it's supposed to work. So it's an eddy current probe. What we intend to do is we use a HoloLens to guide the user through this inspection process to indicate visually all those rivets. Then the user can move the probe from rivet to rivet to rivet. We know when we have a measurement for the rivet because we get this measurement. We can associate this measurement to the surface, and then later we can also visualize all those measurements on the surface. That's it's going to come. This will be ready by the end of the year, September, October, hopefully if everything goes well. So if you like to visit Iowa State, this would be a good time, because then you can see this here. Okay, so let's then a little bit to some other techniques that we use in the lab. There's one topic that I cannot spare you from. I believe you know this because everybody right now in this area works in this area. So I will not call it AI. I will just say, so we work on convolutional neural networks for training, convolutional neural networks for real-time pose estimation. So we have a CNN architecture, a two-stage architecture to estimate the pose with a CNN. The first one is a segmentation stage. The second one is the regression stage. I will also not go into details here. So I believe if you follow the literature or read about this, there are plenty of architectures, plenty of models behind that. CNNs, from a pose accuracy point of view, they are not as good today as at least our 3D feature-based tracking technology is. It's, of course, only a question of time. Another disadvantage is, of course, that we currently need training data. And that's actually where we work on. So we focus a lot here on the need of not having training data. So my lab focuses a lot on synthetic data sets for training and to bridge the reality gap between synthetic data and real data. So most of the time when you train with synthetic data today and when you then apply a network on real data, the performance is not as good as with synthetic data because the images, synthetic data doesn't look like real data. Of course, you can improve the rendering techniques that you use, real-time rendering, photorealistic rendering, and so on. We can also do this. We go slightly a different way. So we have a tool, we call it SetForge. Here, these are actually two tools, SetForge R and SetForge G. The first one is the renderer. It just renders virtual content, like this, here Stanford, the bunny. Like this look like here. We can also render with physical-based rendering, not photorealistic, but physical-based rendering. So we have different render techniques embedded and so on. What we do quite a lot is here in our dataset generation, re-render or we adapt the data to make it more realistic. So what we do is, for instance, we have a histogram matching feature embedded so that our rendering looks like the background feature from a histogram from a contrast point of view. So histogram matching aligns the contrast. We also have a chromatic adaptation filter. So we align the hue and saturation to our background. We can estimate normal map and depth maps from RGB images. These are not real data. No, it's real data. These are not how a scanned normal map or how a scanned depth map would look like, but they're good enough for training. And we also can simulate image noise and have some other filters. So all of this gives us a data set which we can train with, and we are getting pretty good with that. So what you see here on the left is our post-estimation results that we get. The red bunny is our reference bunny. Yeah, I think so. The green bunny is the estimate. And this is without refinement. So we usually use an ICP refinement to get a better pose. But then when we use this on real data, we have sometimes still with a small data set to retrain and to adapt the network to its domain, but it works quite well, what we have. So test object here is our bunny, the red one. And that's what I have. So that's it. This was an overview about what we do in the lab. So again, if I summarize this, it's mostly about real-time tracking, high accurate real-time tracking in point clouds, RGB-D data, so depth and sometimes RGB data, plus normal maps is what we use. We have feature-based tracking techniques. The newer ones are convolutional networks, and yeah, we work in areas like manufacturing, assembly training, guidance. So pointing out what the user has to do next, and upcoming is now the inspection domain. That's what I have. Thank you for your attention.
Fabulous. Thank you, Rafael. It's really great. Great overview and lots of relevant topics. This would be a good time if anybody on the webinar has any questions. You can put those into the webinar control panel. There's a section there for questions, and we will see those. Well, while you were talking, one of the people attending has asked a couple of questions. First one is, you mentioned sort of in the beginning when you were showing the HoloLens tracking that there was some delay due to the Wi-Fi. And
yeah.
Have you looked at any other networks, and do you think there are ways to reduce or eliminate that Wi-Fi lag? And is 5G something that you've thought of or heard about?
Yeah, so 5G, we did not think about that and we didn't use it. So one of the problems that we had here at the beginning was our Iowa State University network. There are a lot of students on this network. So what we did is we replaced it with our own Wi-Fi router here. This reduced the problem to some extent, not completely, but at least we got better with that. But that's what we have done so far. We didn't look into 5G or anything else because the HoloLens is limited or has a Wi-Fi connection. So it was an industry-funded project. So we had to make sure that it works on a factory floor or in a training center. Mm-hmm. So we were limited to what the HoloLens has. And so I'm not the Wi-Fi expert, so if we would have to address this again and reduce this further, I believe we are now pretty good with what we have and it's usable. But if we would have to reduce this further, I would have to contact somebody who does Wi-Fi for a living. Mm-hmm.
So another question is around the software application that you showed, the Tracking Expert. You said that's going to be open sourced. Do you know, or have you selected already the licensing scheme? Is it BCD or MIT?
That's a good question. I would publish this at the MIT license, but I believe I have to discuss this. But we want to make it as available as possible. So I don't want to restrict anybody to use it or not be able to use it because we put a license on it that nobody can work with. So it should be, yeah.
Okay, great, thank you. So in some of your examples and videos, you show image tracking. You show some fiducials. And are you still using fiducials or image markers on objects for tracking?
No, not. We use them sometimes if we want to compare something as ground truth data or as reference data, or if we want a second measurement with a different technique, then we still use optical tracking. But it's just then, yeah, as ground truth data to compare things. If we need an origin, for instance, for the HoloLens and want to place an origin somewhere into the physical world that we know and that we can also communicate to other systems, then we use markers in the lab, yes. They're just quite simple to use. It's very easy to use them. So we also have an AR track system in the lab that we also use for the same purpose. So just to comparison, if we want to compare how good are we in comparison to AR track or others.
Yes, to be clear though, in case people are not familiar with AR track, it's an IR system, I believe, that is a fixed installation in a space. It's quite expensive, but you could sometimes see those in very high-end precise manufacturing.
Yeah, exactly. So that's also, so we have other tracking systems available just to compare what we do with other systems.
Okay, that's great. And there was a question from an attendee that came in a little bit late about the one that you have in your image here, I think the tripod-mounted camera, and how you compare, or would you compare the performance that you're getting on the tripod-mounted versus the any experience or data you have on head-mounted cameras, or the cameras that are on wearable displays? How are you comparing those two, this tripod versus a wearable display?
Not yes and no. So what we cannot do is we work mostly with RGBD camera techniques. So from the first HoloLens, we did not really get an appropriate point cloud to do anything. So that means we didn't really use the data other than for testing. So what we did is we attached other cameras. Here, structured core, no, what was the first one? This is a structured sensor camera, for instance, and other RGBD camera, depth cameras on top of the HoloLens, or we built a mount for Microsoft Tablet for that and just plugged into Microsoft Tablet and used it on that. So these are the mobile devices that we use for that. And from a comparison point of view, it depends on what we want to compare and what we want to see. So if we're just interested in post-estimation accuracy, and most of what we do is we compare it with something different. So with ART or with marker-based tracking, and compare it to our ground truth. So we don't change our comparison technique depending on the devices.
Okay.
It's always the same one.
Okay, good.
So
have you tried any HoloLens 2? Do you have an evaluation unit of that yet?
No, I don't have one right now. I hope to get one as quick as possible.
Right, doesn't everybody? Okay, let's see. I want to take another question. Forward. So one question is, in addition to the Kalman filtering, are you planning, or do you currently use any predictive feed forward for real-time motion tracking? So predictive algorithms to estimate the future position.
Yeah, we have a Gaussian model, based on Gaussian mixture. We don't use this really for real-time pose estimation, but we use this to analyze a sequence of images, and then to predict. So the Kalman filter also predicts the current pose, but not the future. But so we don't use anything else. And I think the Gaussian mixture model is not really it doesn't predict the future, it predicts the current state. But no, I would say we don't use anything else right now. So
Okay.
we don't estimate the next position.
Okay, good. So now a different topic pertaining to the 3D models. So you talked a lot about the use of CAD models as a starting point in some cases, and that you have those for manufacturing design systems, and that the question is, could you explain a little bit how you use those CAD models and what format they are in? Are they are you converting them, or are they in the native formats? And which aspects of the 3D models are used against the point cloud data?
So what we extract from so first of all, to the format, we get multiple formats. So we got data in as DIE Collada files, not CAD models, but then CAD models and exported to Collada. We got FBX, we got SDL, and even IGES files at one point. So the entire piston motor that you saw in between was IGES. So usually we convert them into another file. So what we usually work with, PCD, OBJ, FBX. Then what we have is we have two tools. I cannot, one moment, maybe I can show that. So the first thing when we process it, we need a point cloud out of those. And we have a tool, it's also available on GitHub. That extracts a point cloud. So it takes a file, surface file, and then extracts a point cloud. So that's the first thing what we need. We need this point cloud. So we can then load this point cloud into Tracking Expert. And so Tracking Expert then extracts features out of those depending on which feature descriptor model we want to use. So we have our own variant, but we also implement two other ones from the state of the art that we have. And then it depends on what you need. So we extract this data from this point cloud and store it then into currently an XML file. It's our own XML version of this file, and it contains all the data for Tracking Expert, and that's it. So needs a few.
Okay, so you mentioned before that you use the RGB camera. Are there any cases in which you're using a depth camera or you use depth information?
Most of the time, so we use depth information most of the time. So with RGBD, it's so Tracking Expert is just built around RGBD. So we use sometimes color information if we don't get enough from depth information. So if
any texture, do you ever use texture information to match the object?
Not anymore. So I did this in the past. That we extracted features from 2D from 2D or 3D surfaces, but most of the time it's not. So most of the objects that we have are textureless, and if we go to textures, we now go more into the CNN direction. So we did this in the past, that we use 2D feature descriptors, and if we have surfaces, highly textured surfaces, then we extracted features from 2D surfaces and used them to detect the location of a part. Yeah, but it's not. No, it's really.
It's not what you're working on.
I don't really remember when I had to use them the last time. So we have a project where we still have them integrated, but we also move them out there and go to convolutional networks and features/activation that we get from convolutional neural networks because they give us the same information.
Fantastic. Thank you so much. I think we've gone through all the questions, and when we have made a recording of this, and we will have it up on the YouTube channel of the area, and Mark Sage will send out a message to the attendees. Thank you again, Rafael. This is fantastic, really valuable, and I know that many, many people will appreciate learning more about what your lab is doing. Look forward to working with you soon.
Great, thank you. Thank
Bye,
you all
everybody.
for attending. Bye.
Yep. Bye-bye.